Hello and welcome to Lecture 1 of Sci 93, Laboratory Physics. For this semester, each lecture that we start will have a page like this. It'll outline our objectives for the lecture, which connects to the learning outcomes for the course, and we'll always have a lecture outline with a rough idea of what we are going to cover on this day. Today's lecture is on physics, quantities, and error. So we'll look at why do we study physics, how do we know the things we know in physics, we'll consider the units, conversions, and significant digits of measurements, and we'll finish with looking at approximation and errors. First, let's consider why do we study physics. The study of physics allows us to explain how objects and systems behave, especially in given situations. And we can talk about understanding how airbags work or why the sky is blue, and we can even consider how electron microscopy produces an image. But I like to take a more general view to why do we study physics, and we think about what physics is doing. I like what Galileo had said. The role of physics is to measure what is measurable and make measurable what is not so. We use experiments to provide data that allows us to discover facts that aren't accessible to us. So we measure what's actually accessible to us, then we create calculations that let us understand what we couldn't measure. And the process of studying physics, I think of as examining, yes, but why? We understand results so that we can apply them to future problems. And in this course, I want you to focus on how to apply the knowledge you gain, not just memorizing the steps that I perform to solve one specific problem. There are many different types of problems that we will look at in physics, and if you just try to use that memorize steps version of approaching a course, you'll get stuck on anything that doesn't match exactly that problem. One last thought that we can consider isn't just about physics, but about science in general. And Neil deGrasse Tyson has recently put out a t-shirt that says, to be scientifically literate is to empower yourself to know when someone else is full of, actually, maybe I'll just paraphrase this one. But getting that understanding from physics will help us know when somebody's trying to trick us. Let's think about what physics means directly to your program. So biotech forensics. An understanding of physics and its relation to your field will enable you to use your deeper knowledge to problem solve multiple issues. Now, this could be issues that come up with material handling, like your pipetting and your separations. This can be problem solving issues with some of the tests you run. So you guys will run microscopy tests and photospectrometry tests and mass spectrometry tests and all the other metries and scopies, and understanding the principles behind the physics that lets these tests work will help you understand what you're looking at. These kinds of tests directly connect to what we saw Galileo describe physics as. We can't measure some of the very microscopic subatomic characteristics of a particle, so instead we perform some sort of examination that allows us to measure other quantities. Now, sometimes when we're performing tests, we get really odd results, and having a deep understanding of physics will let us understand when results are reasonable or when they violate the laws of nature. And often when you get a result that violates the laws of nature, that should be evidence to you that something has gone wrong in your test. And with that understanding, you can catch that before reproducing that error too many times. So how do we know the things we know? The study of physics is concerned with describing the interaction of energy, matter, space, and time. It's especially interested in what fundamental mechanisms underlie every phenomena. To determine which fundamentals we know, we have to go through a scientific process. So at some level, there are physicists focused on discovering. So these theoretical physicists use observations and they try to develop hypotheses about the fundamental behavior of our world. And this is the bleeding edge of our understanding of physics and everything that happens. So it starts with they just see something that interests them, and they take an educated guess about why that happens. or they'll make a prediction about what will happen next. And from that, we move into a second realm of physics studies. And this is the proof round. So these are laboratory physicists, and they'll often develop experiments to collect evidence trying to support a hypothesis that a theoretical physicist came up with. Once they find enough evidence to support that this hypothesis is possible, then experimentation will continue, and it'll actually shift focus towards attempting to find evidence to disprove that theory. And as those attempts fail, a theory based on that hypothesis slowly becomes accepted as either a law or a principle. The distinction between those two isn't very important. You can also have experimental physicists or laboratory physicists that look at trying to refine our knowledge of phenomena and fundamental quantities. We have certain quantities like the acceleration due to gravity near Earth, or even the mass of Earth, that we are constantly performing experiments on to try and know these constant values to greater and greater levels of precision. A third area of physics studies is the application. Now, application would be our broadest phase. And this is where we take what we know about our laws and principles of the world, and we apply them to either try and flush out new discoveries, or to test other hypotheses in a different way, or we can even use our fundamental understanding of the universe to verify observations of behavior. This is mostly what our class is going to be focused on and what our labs will be doing. We'll be applying the stuff we learned from our textbook and our problem sets to try and get a deeper understanding of that concept. And we'll also use this knowledge that we have to try and build our own tests. So we'll use observations of known quantities to try and predict quantities for an unknown object. One of the things that's really important about the approach to science is to consider the role of falsifiability. Now, your textbook talks about this a little bit, but it talks around the idea. It's important to remember that experimenters look for evidence of a theory being false, but they treat that theory as true until we find a way to disprove it. So we give theories the benefit of the doubt. Whenever we believe we've designed a good experiment, and you can even apply this to your problem sets, whenever you think you have a good solution to a problem, we have to take time to try and break that experiment or any assumptions that went into the design of the experiment. If we can withstand that attempt to break the results, if we try something that shouldn't fit and see where those results turn up, then we produce stronger evidence to support the theory. We need to briefly consider our methods applied to develop hypotheses and to solve problems, because they're actually closely related. You guys have most likely seen the scientific method before. This is where we start with a question, and that's the same as what the theoretical physicists were doing, where we have some observation and we need to consider why that happened or what's going to happen next. And to do that, we generate a hypothesis, which is our educated prediction, and we use our fundamental knowledge, so we may have to do some research for this stage. And with that, we design an experiment to conduct and then investigate or collect evidence towards supporting or refuting our hypothesis. And once we have all that evidence, we actually have to analyze it. So we have to consider our results and determine what the next step is. Often, analysis will leave us with another question. So analysis will actually restart the whole process over again. And this is the same as our problem-solving method. Problem-solving is going to be very complex, so we need to make sure we have a systematic approach to anything that gets difficult. I want you to consider these 4 steps, and we go through these steps in this order. So we observe, we look at the problem that we've been given, and we start to look at the information and the constraints and the assumptions that are all connected to that scenario that's being described. And once we've done that, we move on and we have to orient ourselves to the problem. So we take time to think and gain understanding and consider the nuances and important pieces of information that we just observed. And we try and wrap our heads around exactly what the problem is trying to ask us to solve. With all of that information in our head, we need to decide on our course of action. So we need to think one step ahead. We need to just determine what we need to do. And as I said, you're anticipating this with what the results will be and what you would want to do with those results. Once you've decided on your course of action, then it's down to the acting stage. You need to carry out that step. And just like the scientific method, we'll turn around and make observations of the results of our actions, orient ourselves to what has changed, decide on the next step, and carry that step out. And as you see, this is a loop. This problem-solving method or decision-making method is often referred to as an acronym, and you'll hear it called the OODA loop. So it can happen over and over and over again. And people who are good problem solvers are practiced at going through these stages rapidly and taking them step by step by step each time, but having an appropriately sized step for each iteration of the process. Now that we have that broad view of physics out of the way, we can begin to look at the quantities section. So the System International, or SI for short, is an agency that looks after managing our units for basic understanding. What's been conducted here is a transition to have our units defined by 7 fundamental constants. So we have the wheel here that shows us that we have Planck's constant, the speed of light, the hyperfine transition frequency of cesium, the elementary charge on a subatomic particle. We have the Boltzmann constant, Avogadro's number, and something called the luminous efficacy. All of these are specific constant values that we use to determine the 7 base units. Of these 7 base units that we use, 3 of them are most common. We have the length, which is the meter, mass, which is measured in kilogram, and time, which is measured in seconds. You should note here that our base scale that we look at is the kilogram, meter, second scale. There are others. There's a gram, centimeter, second scale, but it deals with much smaller things, and some of the conversions are a little different. So we'll focus on using these as our base units. In the wheel at the bottom of the page, we see the ampere, the Kelvin, which measures temperature, the mole, which is a count of the amount of a substance, and the CD, which is a candela, which is a measure of how much light we have. Now, from our base units, we can have derived units. And derived units can be determined through some algebraic combination of the fundamental units. So we could have a consideration of speed, and we will actually next week. And speed is a combination of length and time. We also have force. Force we'll see is measured in a unit called the newtons, and the newtons is derived from the units for mass, length, and time combined algebraically. Anytime you start to consider what units you have from any calculation, this is looked at as something called dimensional analysis. And being able to do that analysis is actually very powerful as a backup check for any work you've done. Whenever we need to express a quantity with units that are different than what we've been given, we'll have to use the unit factor method of conversion. The unit factor method can be broken down into 3 steps, and now these might be slightly different than other ways you've been taught to convert units, but I want you to practice this because it's very powerful. So let's work through these steps with a couple of examples in mind. Let's convert 8.1 kilometers to meters, and let's convert 7,230 seconds to hours. Our first step in the unit factor method is to build a conversion factor with the units we have and the units we want. Now, you guys are going to have a conversion sheet with some of the most common unit factors or conversion factors already there. So you'll just go to the sheet and you'll pull out that information. So in the first problem, we have kilometers, and we know that for every 1 kilometer, that's equal to 1,000 meters. It's usually very useful to take one of the larger unit and many of the smaller unit. In our second example, we know that for every 1 hour, we have 3,600 seconds. Again, if this isn't a conversion you have memorized, it's okay. That one will be on your formula sheet. The second step is to orient your unit factor. So from our conversion factor, we can say one of two statements. We can write this as 1 kilometer over 1,000 meters, or we can write that as 1,000 meters over 1 kilometer. Each of these things are equal to 1, and only one of them is going to be useful to us. So before we determine which one's useful, let's look at the other example where we could say either 1 hour over 3,600 seconds or 3,600 seconds over 1 hour. Now, to determine which orientation is the proper one to choose, we're looking to put the unit we want in the place we want it. So what does this mean? In our first example, we want to end with the units of meters. So we're going to choose the orientation of our conversion factor that has meters on top. So that's this orientation. In our second example, we want to end in units of hours. So we choose the orientation with hours on top. And when that's done, we can move on to our third step. Step number 3 is to multiply all unit factors against the original measurement. Here we only have one unit factor for each of our examples, but you should note that if we needed more than one, we can just keep multiplying on more unit factors until we get the desired conversion. So here we write down our original measurement of 8.1 kilometers, and we multiply that by the oriented unit factor of 1,000 meters over 1 kilometer. Our calculator gives us the number 8,100 as the value, and we look at the units canceling out, and we cancel a kilometer with a kilometer, and we're left with meters only, which is good. That's what we're after. If we look at the second example, we write this out as 7,230 seconds multiplied by 1 hour over 3,600 seconds. We can enter this into our calculator and we get a value of 2.008333. There's a lot of threes that continue on. And again, when we consider our unit conversions, we have seconds canceling seconds and we're left with only the hours. A second strength of the unit factor method is that we never have to try and remember for this conversion, do we multiply or divide? Just being able to work with the fraction we set up here, we can see that this calculation is done by taking 7,230 dividing by 3,600. The final powerful piece for the unit factor method is that if we made a mistake on any of these, we've written out more of our steps. It's very easy to go back and look through to find any errors in setup before we complete our calculation. This is such an important skill that I want to consider 2 more examples. If you are traveling at 2 kilometers per minute, what is your speed in kilometers per hour and meters per second? These are rate conversions, so they're more difficult than just normal conversions. Let's look at part 1. We're going from kilometers per minute to kilometers per hour. So there's a rate unit, which means we may have to consider 2 conversions. On the top, in the numerator of both of these rates, we have kilometers converting to kilometers. So we don't actually have to do any work on that one. So the build stage is actually quite straightforward. Looking at the denominator, the bottom numbers, we have the units of minutes going to units of hours. So our build stage here is that we know 1 hour is equal to 60 minutes. Next, we complete the orient stage. So here we want to choose the orientation so that we have hours in the place we want it. So that means we want hours on the bottom. So we orient that unit factor as 60 minutes over 1 hour. You need to be very careful because we're going to work with minutes and meters. you want to always make sure you write out the full unit of minute, never just an M. We move on to step number 3, which is the multiply stage. So we take our 2 kilometers per minute, we multiply by 60 minutes per hour. Our calculator shows us that that is 120, and our evaluation of our units is kilometers per hour. Does this make sense? Well, let's look at it. If we have a speed of 2 kilometers every minute, and we're now considering how far we travel in an hour, which is a much longer time frame, we should expect to see a much bigger value there. So I think this is an acceptable conversion. Let's look at the example for part 2. Here, we're going from kilometers per minute to meters per second. So in our build stage, in the numerator, we have to convert kilometers to meters. So we have 1 kilometer is equal to 1,000 meters. And in our denominator, we have to go from minutes to seconds. So we have 1 minute is equal to 60 seconds. I'm going to orient these as 1,000 meters over 1 kilometer and 1 minute over 60 seconds. How did I know to do this? Well, I want to put the unit I want in the place I want it. So my final units require meters on top, so I choose the orientation with 1,000 meters on top. And my final units have seconds on the bottom, so I chose the orientation that puts 60 seconds on the bottom under 1 minute. In the multiply stage, we see here that now we have more than one unit factor, but we can multiply both of these unit factors at the same time. So this becomes 2 kilometers per minute times 1,000 meters for every 1 kilometer times 1 minute for every 60 seconds. And we go to our calculator and we enter this in our calculator. So this goes in as 2 times 1,000. And then because 60 is in the denominator, the way we work with fractions, that becomes divide by 60. So our calculator spits out 3.33, and again, we have a lot of decimal places. And our analysis of the units tells us that we are left with meters and seconds because we have a kilometer canceling a kilometer and a minute canceling a minute. That's 2 examples in a row now that have left us with many extra decimal places. How many decimal places do we include? It's quite common that when we do calculations, our results will contain more digits than we can trust. The final result of any problem should be rounded only once and only at the very end of this calculation. And it should have the same number of significant digits as the least precise input number. The rules for counting significant digits can be expressed in 4 statements. So rule number 1, the digits 1 through 9 are always significant. So if we look at the examples, 623, which has 3 significant figures, and 1.931, which has 4 significant figures, we can see that it's quite easy to count significant figures that are the digits 1 through 9. If rule 1 covered the digits 1 through 9, that means the only thing left to consider are zeros. With zeros, it matters where the zero happens. So it takes 3 rules to cover this. Rule number 2, leading zeros are never significant. Leading zeros are the zeros that are to the left of all other digits. So in the example 0.623, we have significant digits 6, 2, and 3, but we have a 0 to the left of those, which is a leading zero, so it's not significant. There's only 3 significant figures here. In the example 0.0004, we see we have a 4, which is significant, and 4 zeros to the left of that, none of them are significant. So we have 1 significant figure for that value. Rule number 3, our trapped zeros are always significant. Trapped zeros are zeros that are contained between 2 digits that are already significant. If we look at the example 62,003, the 6, the 2, and the 3 are all significant, and the 2 zeros are trapped between significant digits. So all 5 of the digits here are significant. Let's consider the example 0.1009. Well, by rule 1, the 1 and the 9 are both significant, and that would make the two zeros here trapped, so they will be significant. But the 0 to the left of the decimal place is to the left of all other digits, so it's a leading 0 and it is not significant. This example has 4 significant figures. Rule number 4 is trailing zeros are often not significant unless they have a symbol to tell us they are. So this is the most tricky rule. Trailing zeros are zeros to the right of all other digits. The symbols we're looking for are either a decimal place or an overbar. So let's look at the example 62,300. In this case, the 6, the 2, and the 3 are again all significant. The two zeros are to the right of all other significant digits, and there is no decimal place present, so these are not significant, and this value only has 3 significant figures. What about the example 500.00? Well, the 5 is a significant digit, and the 4 zeros are to the right of it, and a decimal place is present, so all 4 of them are significant. This value has 5 significant figures. What about 500? Again, the 5 is significant. The 2 zeros are to the right of it, which means they are trailing. Again, we see no decimal place, so this is non-significant zeros, which means we only have 1 significant figure. What about 500 with a decimal place? Well, in that case, the decimal place makes the zeros to the right trailing zeros that are significant, and we have 3 significant figures. Let's make this a little tricky. How could we show the value 500 with 2 significant figures? If you look, if we put a decimal place, then that would give it 3. So this is where we consider the overbar. So if we put an overbar over the middle 0, that means the 5 is significant, and the 0 with an overbar is significant, but the 0 to the right of that is not. So an overbar to the left of the decimal place signifies the rightmost significant of the trailing zeros. So if there's a trailing 0 to the left of an overbar, that makes it a trapped trailing 0, and it can be significant. And if we have an overbar to the right of the decimal place, that use of an overbar signifies a repeating decimal, so it's not usually used on zeros. The other way you could show 2 significant figures is to convert to scientific notation. And we will use scientific notation a fair bit in this course, so it would be a good idea for you to review that from your math course. The number of significant digits we have in a value that we measure will be determined by the precision of the tool we measured with. Tools with different precision levels will have different numbers of significant digits. So when we express a measured value, we include as many digits as we can read on the tool. So these are the marks on the tool, and only 1 estimated digit. And by convention, we estimate to half the smallest increment. You should recall that this is also the rule for determining the measurement uncertainty with a tool. So let's look at an example here. If we try to read the length of the blue line, seeing that it falls between 6 and 7 centimeters, we can look even closer to see that it falls between the 6.7 and 6.8 marks on the tool. And because the smallest increment is 1/10 of a centimeter, we can say that the uncertainty is plus or minus 5/100 or 0.05 centimeters, which means we can record a value of 6.7, that's read directly from the tool, and estimate another half an increment. So 6.75, and including the uncertainty of plus or minus 0.05 centimeters. Let's zoom in on another version of this tool. If this tool had more precise increments, we could provide a more precise reading, meaning more significant digits. So if we included 1/10 of a millimeter on the tool and looked closer, we could see that this line would measure 6.77, read directly from it, and estimated to be half an increment, so 6.775 plus or minus 0.005 centimeters. Now, many of the values we're going to work with fall in the metric system. This means that rather having seemingly random conversions like the imperial system, When we switch the scale of our unit, we'll move some order of magnitude, and that just means some multiple of 10. When we look at any metric relationship, we'll have a prefix, which is just a little collection of letters that goes ahead of the unit and that we read out. And each prefix has an associated symbol, and these all represent an order of magnitude. So we were just working in centimeters. So this is the prefix centi on the base unit of meters. If we look at the chart, the symbol C lines up with the prefix centi, and it represents an order of magnitude of 10 to the negative 2, which means if we wanted to convert our value of 6.75 centimeters from the previous example to meters, we could replace the centi with 10 to the negative 2 and say that this was measured as 6.75 times 10 to the negative 2 meters. Let's look at another example. If we have 45 kilograms, we have the symbol kilo or K attached to the base unit of a gram. If we replace the kilo with its order of magnitude of 10 to the 3, that means 45 kilograms is equal to 45 times 10 to the 3 grams, or 45,000 grams. Anytime you need to make conversions using the metric chart, this will be on your formula sheet, you simply can move to the base unit and then back to the other unit, or you can count the number of factors of 10 that you have to move by seeing how far away you are from the other unit. Note that this is set up so that units at the top of the chart are much bigger than units at the bottom of the chart. So you would take one of the units closest to the top and many of the units closest to the bottom. When we're working with really large and really small orders of magnitude, it's often difficult to conceptualize the significance of any value. It's hard to picture what it is. So one of the ways we deal with this is to relate the value to something that's more perceivable. So let's consider this with time. I'm sure each of you are quite comfortable with how long is 1 second. Now, what if we jump up one order of magnitude? What if we jump up and say, how long is 10 seconds? That's just long enough for an awkward silence. Let's jump another order of 10. And we're trying 100 seconds now. I'm not going to make you wait, but many of you would probably be more comfortable trying to figure out this time scale in minutes than 100 seconds, and it's approximately 2 minutes. Let's do some more approximations continuing up. Let's look at 10 to the 3 seconds, or 1,000 seconds. How long is that? Well, it's approximately 16 minutes. And if we jump another factor of 1,000, you'll see that in our metric chart, we actually move by factors of 1,000 after the first two. We're looking at 10 to the 6 seconds. So this would be a megasecond or million seconds. And it might surprise you to see that we have now jumped to a time interval of 11 days. Let's jump again to 10 to the 9 seconds. So this is a billion seconds or a gigasecond. And I'm sure that very few of you have actually been alive for a billion seconds, as this time frame is almost 32 years. This is the process of approximation. We are essentially comparing very large or very small magnitude of values with a different quantity, so we are converting to a different quantity that's easier for us to picture or conceptualize. The book goes through this by comparing heights of buildings to heights of people, and there are many other ways that you could work through this. Let's make one more jump. Let's go to 10 to the 12 seconds. So this is a terasecond. Can you guess how long 10 to the 12 seconds is? Well, it's 1,000 times our previous, so it's approximately 32,000 years. So note that 1 trillion seconds is longer than the time that we believe civilizations to have existed. We didn't talk about this. We talked about the precision of a measuring tool, but we didn't talk about the accuracy of the measuring tool. Often when we're talking about accuracy, what we're talking about is how close to a true value we get. Now, anytime we take a measurement, we know that there will always be some level of error, which means there'll always be some level of inaccuracy. Our job is to find ways of making calculations that will mitigate this level of error. When we consider error, there are typically three ways we consider error. The first is mistakes, and in measurements and calculations, mistakes are not considered as acceptable errors. When these occur, experiments will need to be redone to correct the mistake. It is not acceptable for experimenters to just shrug off mistakes in the setup or data collection phases. You should always take care to assure that the correct experiment design and accurate data collection have been completed. Other types of errors are acceptable, not in that we want to just ignore the error, but that we can work with the error that we've been given. So systemic errors often result from experiment design, but they can be predictable, acceptable, and even corrected for in calculations. Often, when we have a systemic error, this can lead to the discovery of a previously unknown aspect of an interaction. Other versions of systemic errors could be that experimenters have recorded all of their data as centimeters instead of millimeters, which can easily be adjusted by including a conversion factor in your calculator. Some planets have been discovered simply because, as we went to predict the orbit of other known planets, they diverged from the predicted path. And that consistent divergence is what led us to predict the existence of Pluto. The last type of error is random error. This can also be considered normal or natural, and it results from the natural variations that are often explained with statistical understandings. These types of error can also be dealt with, and one of the main ways we deal with them is to complete repeated trials of an experiment and then use simple statistical calculations to mitigate the amount of error. As we said, the reason most experiments perform many trials is to provide extra data to try and estimate out the random error levels in an experiment. The first method for reducing the effect of random error is to take the mean of all the values. This is the average, so this is represented with the X bar symbol, and it is often the sum of all your values divided by the number of values, though it's more than acceptable for you guys to just use the average function on your data set in Excel. We also use the variance of the data set to inform us about the uncertainty in our calculated value. So we use the standard deviation, which again, you would calculate using the sample standard deviation function in Excel, and then calculate something called the standard error of the mean. So this would be S subscript m, and it's calculated by taking the standard deviation and dividing it by the square root of the number of measurements taken. This standard error of the mean is used to calculate the range of our predicted value that we're trying to obtain. So we would report an experimental result with uncertainty of X bar plus or minus the standard error of the mean. We've mentioned that some errors are acceptable. How do we determine what's an acceptable amount of error? I'm sure you would agree with me if I said 1 centimeter of uncertainty isn't really a lot to worry about over a 1 kilometer measurement, but if that 1 centimeter of uncertainty was existing in a 10 centimeter measurement, that is a lot. So in practice, we think about error in terms of percentages. Now, for each experiment and each application, the percentage that's acceptable versus not acceptable will be different. But here are several ways you can calculate that percentage of error. The first is to consider experimental error, and that's going to compare that standard error of the mean to the mean itself, and then multiply by 100. We could also consider a percentage difference in experiments where we've calculated a value and we have a known, accepted, or true result. In this case, we would compare that mean, subtract from it the accepted value, and divide that again by the accepted value. This is a great calculation to use if you're trying to calibrate your experiment. If you are conducting a simple experiment like massing a known object, then if you already have a trusted mass for that object, you can see if your scale is accurate. And if it isn't, by what percentage it's off by. That percentage difference is a percentage of the accepted value, which when we don't have a known value in the situation, we wouldn't be able to apply that. So when we're using an unknown value in an experiment, we want to use an adjusted prediction equation. What typically happens is we'll go and we'll do our experiment on the known value and we'll calculate the percentage that it's off relative to the measurement we took instead of the accepted value. This percentage we can then take to the unknown value and use that to adjust our prediction up or down. So if we had an adjusted prediction percentage of plus 10%, that means we know every measurement we take is 10% greater than it should be. So when we take a measurement on the unknown value of 100, we know to adjust that down 10% and suggest that our prediction should be 90. Now, we haven't done many calculating examples today, but you guys will begin assignment 1. And we want to make sure that everybody's on the same page as far as how to communicate solutions to problems. So to do this, we want to make sure you're employing a method so that you have a system. One of the methods could be referred to by tons of different names. But for now, let's just stick to one and call this the GRASS method. And GRASS represents G for given. And in the given stage, what I'm expecting you to do is identify and list all of the information that's given to you in the problem. This includes acknowledging any of the unknown values in the problem, so the thing you were asked to solve for. The second part of this method is the required phase. In the required phase, you're going to list out the tools or equations or concepts or known constants that you're going to require to calculate your solution. The A stage is the application stage. This is where you apply all of the things you've listed in your solution. So you're going to combine any equations you have and constants you have, and if needed, rearrange and substitute into other equations before moving on to the substitution step. So the substitution step is where you enter all your given values and you evaluate the equation that you've created. So the substitution step includes solving. So you're going to end the substitution step with a value. The second S is the statement. That value isn't useful to anybody until you make a statement that puts your final numerical value into the context of the problem. It's in the effort to make this more clear, I want to express that just telling me an answer 7.5 is not an answer on its own. Without any context, I have no idea what that means. And you haven't done anything to show me that you know what that number means. So by completing the statement step, you're trying to show me that you understand the tools you're using and the problem you've been asked to solve. One of the biggest tips I can give you here is that every time you complete a problem, you need to ensure you have answered the question you were asked. So sometimes you're not just asked what is the acceleration or the distance or the force, you're asked if some consequence will occur. So you determine what value that means you need to calculate, but you also need to answer the question by saying either yes, the consequence will happen, and you need to provide reasoning for why you think the consequence will happen based on the results of your calculation. This brings us to the end of our first lecture. So we've established some of our fundamental concepts that we need to proceed into our future discussions. So we examined units and ways of converting them. So this involved looking at the SI system of units, looking at the unit factor method of conversions, and the metric prefix system table that you will get to use. We also considered the effects of precision on our calculations, and this came up in our discussion of significant figures and precision and accuracy. We went on to introduce the concept of error and look at all of the different calculations we can do to work with the amount of error we have. And finally, we established a method for communicating problem solutions, and that was that GRASS method: given, required, application, substitution, and statement.